It's awful sometimes.
I'm sharing the screen. Sharing my desktop.
Hello, everybody, and welcome back to Hangout with CERN. I'm Steve Goldfarb, and I have with me Patrick Koppenberg of the LHCb experiment. And today we're going to do Hangout with CERN, the beauty experiment. It's all about LHCb, the beauty experiment on the Large Hadron Collider. We also have with us, joining us from the beauty conference up in Edinburgh, we have Greg Cohen, Daniel Craig, and Augusto Alves. Hello, gentlemen. How is it up there in Edinburgh?
Hello there. How are you?
Hello.
Hey, everything's good here.
Sunny as usual in Edinburgh, I imagine.
Gorgeous today. Gorgeous.
Excellent.
The
and
one
finally,
is sunny.
And you're at a beauty conference, so you're looking at different types of cosmetics and things like this.
Like Pantene and.
Excellent. All right, we're going to get back to that. We also have with us our social mediator, or our media socialite, Tara Shears is joining us. Tara, where are you?
Hi, I am in sunny Liverpool, so I'm a little further south than Edinburgh, but I'm not quite as far down south as you in CERN.
Okay, very good. So we're here at CERN. I'm in the LHC. Patrick's out in the universe somewhere floating about. And we're going to talk to you about beauty. We're not going to talk necessarily about the beauty of cosmetics. Instead, we're going to talk about a particular quark, one of the 6 quarks. And this is the 5th most massive of the quarks, some might say heaviest, one of the heaviest. It's the heaviest quark that actually couples with other quarks, right? It stays coupled before it decays.
Yes.
That's safe to say. There is something much more massive called the top. But it just doesn't hang around with other quarks too much. It just decays too fast. But as a result, beauty, otherwise known as the bottom quark, also is something which is very useful to study. Right? It gives us windows on different types of physics. It's a very, very interesting quark. In fact, what I would like to go to, before we get started with our questions from Tara, is our trivia question. As long as we're talking about this thing called the quark. The trivia question is this. It goes back to 1977, before anybody here was born except me, basically. 1977. During that year, there was a small team of researchers. They were all small teams of researchers back then. Now we're 3,000 people. Back then, there was a small dedicated group, and they were in a laboratory up in New York, Long Island, called Brookhaven National Laboratory. And while they were up there, they were studying something which was relatively new. They were looking at proton target collisions and at the stuff that comes out from that. And they found out that by looking at the products of these collisions and by looking at the angles and the momenta of the particles that come out, they could figure out if there was something decaying to them. That's what we continue to do to this day. They were using electrons and positron pairs to do this work, and then they had the bright idea of let's change that and let's start looking at muon pairs, a positive muon, negative muon. And by making this change and changing their equipment to do so, they could suddenly get much more data. In fact, 1,000 times more data than they had in the past. They went back to do the experiment they had been doing before, and they saw a very nice thing. So the question is, what discovery did they make? And who was the leader of the group that made that discovery? And for an extra bonus point, what phrase that makes all particle physicists cringe came from that person who was the leader of the group? Okay? I just added that in there, but I think that's a good question. How do they get your answers? You give your answers. That was Kate Carla, our producer, saying, Steve, they don't know how to answer you. They can't shout into their computer. No, what you have to do is to either go, if you're watching this on your YouTube page, type it into the comments. Or if you happen to be on Twitter, use the hashtag either AskCERN or hashtag HangoutWithCERN. Type in your answer, and the winner gets an amazing prize, this being the last week that we're going to be doing Hangouts for the summer. We're going to come back again in the fall with them. Okay? So that's the trivia question. We look forward to seeing if any of you can get the answer to that. And now I want to go to Tara. Tara, give us a really good question.
Right, I have just the question to get us started. So this is a question that comes from YouTube, and it's from somebody called Awkward Quark. Don't let that put you off the question. It's a really good one. So Awkward Quark wants to know just why is it called the beauty quark, and what's the importance of it? What's so special about it?
Okay. Well, Patrick, let me come to you with that one. Why is it called beauty? What's so
Well,
special?
the true answer is I don't know why it's called the beauty quark. There have been several attempts of giving names to quarks, but it's clear that historically there were two quarks. Yes? There are two quarks that that make up all the matter we know, protons and neutrons, that are now called up and down. And then suddenly people start to find some particles that didn't fit that were then called strange. So then later on, when the quark model came, the quark explanation to particles, they called this quark that was in these particles the strange quark. That was the quark giving strangeness to particles. But then there were predictions of other quarks, and they tried to follow this pattern of giving funny names. So the next one was called charm, which is very charming. And then the two next were called bottom and top. And some people wanted to relabel that as beauty and truth, which sounds better. And for historical reasons, I don't really know. We in the beauty community like to talk of beauty rather than bottom. But the people who study the top quark, they call it the top quark and not the truth quark.
So we have top and we have beauty now. Otherwise, you guys would be up there in Edinburgh at the bottom conference. You'd be at bottom 2014. I think I see the reason why.
Probably, yes, probably.
We chose beauty. Truth, I don't know. Truth would have been very nice too. We haven't discovered the truth quark. But hey, you know,
single truth event.
It might have been ambiguous. Scientists have discovered truth.
Yes,
that's what we're trying to do all the time. So,
so we've discovered beauty, definitely.
We discovered beauty, and we discovered it back some time ago, a long time ago, and now you're studying it. So maybe I can go up to Edinburgh. Gentlemen, tell us what you're learning at the bottom. I mean, the beauty day 4 of the beauty conference. What kind of results has LHCb been presenting there?
Well, today we've been discussing some of the latest results on the rare decays of B quark or B mesons. So the B meson is the combination of a B quark and some lighter quark. So these are really interesting things to look at. You can study very rare processes that only happen 1 in a billion times for each B meson you have, and we look for these really tiny signatures of these B decays, and we're looking to see if we get more of those than are predicted by the theory, and that may indicate some maybe new physics, which is interesting for us to find. So we're getting the latest results from LHCb and also the other experiments at CERN on these really rare B decays.
So, I mean, it's really useful that you guys have a lot of data.
Yeah, huge amounts of data. Yeah.
You've collected not just a few B quarks, but many B quarks. Okay, actually, I want to put you on the spot. Could you estimate roughly how many B quarks you guys have seen?
How many B quarks we've seen? That goes in the thousands of billions. Now, unfortunately, we cannot collect them all. So if you count the numbers that that went into our detector and could be reconstructed, this is getting into several billions, since we have something like 10, 20 E sub S decays to 2 muons, which has a probability of 3 in a billion. So you can calculate that you need a few billion to start from in order to see these 10, 20 candidates. But most of them we throw away immediately because we cannot afford to collect them all and to store all that data. So we need to make very tough choices.
To keep interesting ones.
Yeah.
So when you say things like B sub S, just to make it clear, this is our jargon for saying that you have a B quark and a strange quark with it, right? So usually when we say just B, then you have either an up or a down quarkus with it. B sub S has strangeness. B sub C has charm with it. And then you can have a state where you have a B and a B bar.
Yes. Yep. And since we're not consistent, we call that the bottomium. Which is much nicer, much easier to pronounce than butemium.
Okay, so it's practicality that goes to the name.
Yes, exactly. So this is a combination, but this is much shorter lived than the other mesons that you mentioned, the B sub C, the B sub S, because the two B quark can annihilate, they can eat each other and then decay to pairs of very often it's pairs of muons. This is what is most useful for us to detect them, but it can be anything else. So these are more special kind of mesons that we also study, but it does not allow us to really understand the properties of the B quark itself.
Okay. So you're trying to understand the properties of the B quark. So there must be some interesting things. I understand that Daniel up there has presented or is going to present a very interesting result that's very recent that's come out involving B quark. So what have you got, Daniel?
Yes, so we presented it Tuesday morning, actually. Basically we've made the first observation of a heavy particle, so something containing a charm quark. So not actually a beauty quark in this case, but it's related. Bear with me. With a spin of 3. So to just bring people up on the term spin. Spin is this fundamental property of particles, such as charge, for example. You have all of these fundamental particles which have spins of a half or 1, and these can be combined in ways to give things with more spin. And you can kind of the historical name comes from the fact that to all intents and purposes, if you do experiments, these things look like something that's spinning, but we know they're not actually spinning. It's just a property that we can measure. But this state, it's exciting because this particle, it's the D sub S 2860. So I'll break that down. The D means it's got a charm quark. The sub S means it's also got a strange quark. The 3 means it's spin 3, and the 2860 is its mass in these units we use, MeV. Now the way we went about determining the spin of this is actually we looked at the decay of a B sub S meson. So this B sub S actually contains a B quark and a strange quark. And we looked at this decaying into 3 particles, a pion and a kaon, which are made of light quarks, and then the D0 meson. Now this has a charm quark in it. And the thing is that this decay can happen in kind of 2 stages. So first, your B sub S can decay into the pion, and this short-lived state, which is one of this set of states called the D sub S star. So here, the D again means you've got a charm. The sub S again means you've got a strange. And these stars are unimportant. We'll forget about that. These are the D sub S stars. Now these are very short-lived particles, which then this decays on into the D0 and the kaon that we see. So the interesting thing here is that imagine we're sitting on the surface of this D sub S star, and it's about to decay. Probably not the safest place to be, but imagine we are. Now we can see off in one direction, we can see that pion flying away. And just as it decays, we see the kaon it decays into also traveling off in another direction. Now we're physicists, we like to measure things, so suppose we measure the angle between those 2 directions. Now if we've just got one decay, that's just an angle. But in this case, we've seen hundreds of these decays. So we can look at all of these angles, and we can see a pattern in the angles we see. And actually, I think we've got a helper here, but yes, it's that. Technical difficulties. This pattern, it turns out that this pattern depends on the spin of this short-lived state. So we can look at this pattern, and we can match it up to the patterns we expect to see, and we can determine the spin of the state. And the exciting thing here is, if you just look at these black points are the actual data that we're getting out of the detector, and these lines are the possible things that we might expect to see. So we might expect to see something with spin 3, we might expect to see something with spin 1, and these are this green line and this red line. And what you can actually see is the data agrees very, very well with the case where we have something with spin 3 and also something with spin 1. So previously, people had seen a particle here which they dubbed the D sub Sj, where the J means we don't know what the spin is. And actually what we've discovered is it's not that at all. It's actually two different particles. But on top of discovering a new particle, it's also exciting because, as I said before, this D sub S3 is the first spin 3 particle that contains a heavy quark, so either a charm or a bottom. In this case, a charm. And in fact, it's also the first time that anyone's seen a spin 3 particle coming out of the decay of any particle with a B quark in it. In this case, the B sub S. So it's all very exciting.
Well, okay, so let me, for those of you who are preparing for the quiz that we hold at the end of the show, let me do a quick recap here. So on that plot, what we saw was that people had predicted that curve beforehand, and the data matches very well to the fact that they found a particle of spin 3 and spin 1. Now, wow. To step way back, fundamental particles, as Daniel said very clearly, the fundamental particles that make up matter have spin half. We call them fermions, right? Fundamental particles that carry forces, up until a few years ago, always had spin 1. These are fundamental particles. We did just find a couple years ago this funny particle which has spin 0, which we call the Higgs boson, meaning it has no orientation, it doesn't add up to angular momentum anyway. So this is what we have. These are our building blocks, the fundamental particles. But the particles you're talking about here are constructed from some of these. So then, by putting together a couple of these spin 1 halves, you're ending up with a spin 3. So you're saying the reason for that is they're in some sort of excited state. That kind of reminds me, if I think back, just a couple years ago when I was in high school and had a chemistry course, we actually had to learn something about the hydrogen atom. And the hydrogen atom can get excited, and its electron goes around the proton, and it can go to different excited states. And if you see these beautiful images here, those are all the different excited states. So a spin 3, in that case, I guess was some sort of, let's see, there was S, P, and D, so I guess the D orbital. So you have sort of a d orbital kind of state between an L.
S is
0. L, S is 0, yes. Oh, what am I doing? Yeah, S is 0, S 1. And, right. So I'll give up all that. Forget about the quiz. I won't pass the quiz. So really, so it's what is the, what would you call that? It's not like a 1D state of the B quark, the D. I'm sorry, it's a C quark, and the S quark.
Yeah, I don't know how we would actually call it.
Yeah. It's the 1D because
1D. 1D.
Yeah.
See, I'm not crazy.
Yeah. Okay. You're right.
1D.
It's 1D. Excitation, and then you get another half from each of the quarks.
Yeah, each of the quarks you have to add on to it. Okay. So you were right, and I was right.
Yep.
So there you have it. So you're adding these quarks together, and so the things you have to remember in this, there's a lot, but they're composed of a couple different quarks. The name D is very interesting to add one more element of confusion. The name D means that
contains a C quark.
It means it contains a C quark.
Yeah.
Because capital C was already being used. Okay, but there you have it. So D sub S, and it's an excited state. So congratulations. That sounds like it's a first measurement. You must be very excited about presenting that and having that as your analysis work. And you know, how are Greg and Augusto going to top you? Let's see. if what we'll do is we'll give them a question. So maybe we can go to Tara and find out if you have another social mediate question, medial social question for us.
We are getting lots of questions coming in, particularly because people are really interested in what makes beauty quarks special. In fact, what makes the third generation of quarks special? But the first question that I would like to ask comes from Twitter. It's from Sparsh Yoshi, and it's about the beauty quark. And Sparsh asks, the beauty quark is an exotic because it decays. So do beauty quarks always decay in something that's exotic, or do they decay in normally seen particles? I'll answer that one.
Okay, who wants to give a shot? Patrick?
You
want to read?
or setting.
Okay, so the beauty quark. Don't rephrase it. Don't rephrase. I'm getting some sort of.
Yeah.
Maybe you'd like to rephrase it and answer it.
So what I understood is whether the beauty quark always decays into something that is exotic, or also into other particles. Well, actually, what we call exotic are very few particles. These are the particles that are not fitting in the quark model. So we know that all the matter we know made of quarks is organized in mesons that are made of a quark and an antiquark. So these B mesons are mesons. This DS3-2860 is a meson.
Mm-hmm.
And then there's baryons, proton neutrons, that are made of 3 quarks. And then there are some particles that we've discovered that don't fit that, and which are probably made of more quarks. So that's tetraquarks, for instance. But they're very rare. That's very rare that we actually see a decay of that. Most of the B mesons, 99% of the time, the B quark goes to a charm quark. So there's a D meson involved, and then something else that may be an electron, a muon, or a pion, a kaon, some light particle. So this is the typical path, and this typical path is very, very well known. We are studying this, but more to understand the behavior of these quarks, how they interact with each other. It's not where we hope to find new physics. It's more in the rare decays where we expect to find something that is not predicted by the standard model. Mm-hmm. But maybe we come back to the exotics, because this is the other exciting results that we have at the beauty conference.
Who would like to? Who in Edinburgh would like to talk about the other exciting result?
Do you want to say something, Augusto?
We say.
Yeah, so something that we had, well, a couple of months ago, and Augusto presented this week, was the confirmation of an exotic type of.
Oh yeah, can you guys take down your slides so we can see your faces?
You want to? You sure?
Yeah, we want to see your faces.
Yes.
Yeah. In a nice room there with a painting behind it.
Yeah. So we had the first. So we look at the decay of B meson, and we find that it decays into some exotic state, which is actually a combination of 4 quarks. So as Patrick was saying before, the basic model predicts, or we know many examples of 2 quarks together, or quark anti-quark, examples of 3 quarks together, and now we have this evidence of 4 quarks combined together into some resonant structure. So that's really exciting because it's not really been confirmed or seen before, and we now have really good evidence within LHCb of this state. So
it's very interesting because we have learned like the physics, always thinking about the possibility that we would have hadrons formed by quark and antiquark, we call mesons or a baryon, like Patrick told, formed by three quarks. If we found the possibility to have also tetraquarks was predicted many years ago, and it was very important to us found it because if we could not find it, would be a sign of some problem with the theory behind it, with the standard model, because it was predicted to exist. On the other hand, it's a new way to understand how the mass can be put together, how we can organize the matter to have a new aggregate of matter in the universe. And it's very important because it's a lesson to us that not always the nature is choosing the more simple way to organize the things.
This is really the first evidence to see that these four quarks were together.
Well, it was first seen by, there was evidence by an experiment in Japan called Bell. So that also links in with, beauty, you have beauty, Bell.
Okay.
They also studied, this decays of B quarks. In fact, Patrick was a member of that collaboration before he joined LHCb. But yeah, they had the first evidence of this four quark state, this tetraquark. But then it's not been confirmed until very recently by LHCb. So we have much data, like you mentioned before, and that allowed us to really understand what was going on with this guy.
We also performed a very interesting analysis because we tried to explain the signal we was observing without use the idea of a tetraquark is present in the data. Okay, let's see if we can understand it in terms of more simple and existing things. Of the existing physics we have. And we could not explain our data from this point of view. And so we performed what we call a model dependent analysis. This analysis where we put everything we know with fact about the physics, and we included the presence of this new particle, the tetraquark, and we found it to be very, very, very strong signal, and we could explain our data very precisely.
Okay. So the evidence is really pointing to this thing being a four-quark state.
Yes.
And will more data help you out? You're gonna get much more data, I assume, in the coming year as we go to higher energy. Will that help you out, or is it limited by systematics?
No, more data will help us out because we see it in one decay mode. We see the decay of that tetraquark, but now we need to understand whether there are other possible decays. Bell claimed that they see it in other modes. We need to see if we can confirm that, and also look for other decays. Now it's really about understanding what this particle is and how it's formed, and this is best done by studying the various decay possibilities.
Sure.
So far, it's only one decay that is really very well established.
I think it's important to note. I'm going to head over to Tara in a second, but I think it's important to note here that we claim the standard model is all done. We found we found the Higgs boson. Everything is complete there. But there's this whole field that you guys are studying, which is really QCD, which is very, very difficult to predict.
Yes.
It's very hard to do the calculations for this. All you can really do is measure this area. And so there's a huge amount of work still in there to so-called complete our understanding of the standard model. And that's our new area for discovery. The way discovery goes here is not like the Higgs boson. That was a fluke. Right? It's really rare that we know, okay, there's going to be something here. Now, we're doing what we usually do, which is we don't know what's out there, and so we take the model we have and we're going to test absolutely every corner of it. And this is one of those corners, and you guys have a lot of work to do. So I think now's a good time. We're going to go to Tara and get another question from social media.
Okay, this is a much more general question. So far we've just been talking about the properties of the beauty quark, which is one of the members of the third generation of quarks. And Antipodean Reason, I hope I pronounced that right, on YouTube, has asked, why do nature's particles come in three families? What's so special about that? Why should it happen?
That's a very good question.
That's a very good question, and I'd love to know the answer.
Yeah.
Why do we have three families? It's not only in the quarks, it's also in the leptons, where we have the electrons, the muons, and the taus, and their corresponding neutrino. They also come in three. And we also don't know why it's three. What we know since already quite some time ago, 40 years now, the fundamental paper by Kobayashi and Maskawa, who showed that actually if we want to understand the asymmetry between matter and antimatter, if we want to explain this as the consequence of decays of particles containing quarks, then we need at least six quarks, at least three families. So at that time, that was an amazing postulation at that time, because at that time only three quarks were known. The fourth one, the charm quark, was postulated for other reasons, and they said, well, we actually need the number 5 and the number 6.
Yeah.
And this happened then to be confirmed by experiment. And so far, all the asymmetries between matter and antimatter we know in the experiment can be explained by this transition between these 6 quarks. But if you have less than 6 quarks, it does not work. You need these additional quarks that were then all discovered later on after their prediction, and they got the Nobel Prize 3 years ago now, 4 years ago.
Yeah.
It was fairly recent. They had to wait for a long time until they got the Nobel Prize for that.
But it's been essentially verified. And that is a very fundamental question. You're thinking like a scientist. Thank you for that question. We're all asking that question, and we don't really know. I can reveal my age by noting that my thesis was on discovering that was it, essentially. From the data that we had at the beginning of LEP, a long time ago, there are seemingly only 3 families, at least, of light particles, unless there's something really, really massive out there. There's 3 families, and we don't know why. We don't even know why. We don't need them necessarily, except that we see these asymmetries. That's all. Okay, Tara.
Okay, following on from that question, I have another one from Twitter, from Martin on Twitter, who says, why do we have different conferences for top and bottom quarks? I think he's trying to suss us out as people who just like going to exotic places to have conferences. But really, at the root of his question, he wants to know, are top and bottom quarks really that different to justify completely different areas of investigation? What's the deal there?
What do you guys up in Edinburgh think about that? Would you go to a top conference, or do you feel specialized in bottom? And why is there a difference between these conferences?
I think it's to do with how we described the top and bottom earlier on. I mean, the top doesn't combine with other quarks to form these mesons and baryons, so that it has it leaves completely different signatures in the detector compared to the decays of the B mesons that we study at LHCb. So they're quite different specialities in some sense, and they have different techniques to extract the signal from the data. So that's a kind of different focus of the top is also much heavier than the B. You know, it's like 20. 20. Yeah. So that also gives a different energy regime where you meet these different methods to understand what's going on.
So yeah, I think I mean it's interesting that we're so specialized as to have conferences for different quarks, but that's the reality. Is we're getting deep down into the details, and there's a huge difference. The top quark, as we mentioned early on, doesn't couple with other quarks. It doesn't have time. It dies too quickly. So, but studying the top gives you a lot of interesting things, and even tells you information about the Higgs, because it's so massive. It's the thing that's coupling with the Higgs most. And studying that is often done to try to learn about spontaneous symmetry breaking mechanisms and things like that. So it's really a different kind of physics between these quarks, and we have many different conferences, and different topics. I didn't go to. I was just at a different conference where the primary thing to talk about was the Higgs boson and physics beyond the standard model, and that was also attended by 1,000 of my best friends.
Yes.
Well,
I was there.
You were there, yeah. Yeah, see, 999. So let's see. Well, I think it's probably time now, as our producer is slyly indicating to me, to find out from Tara, has there been anyone who is capable of answering my very difficult trivia question?
No, Steve, I don't know. I think you just stumped everybody. And perhaps people didn't realise that we were giving them an incredibly large clue as to the answer with the subject of this hangout. So no, nobody has managed to guess the answer to a trivia question and get your wonderful prize that you mentioned.
My goodness. Even though we did have plenty of hints throughout the show, you mentioned that we find B quarks by looking at their decay to muons very well. Yeah. The question one last time, in case anyone's quick on Twitter, you're giving me the answer. Okay, we're going to give the answer, so we get the prize this time. Sorry.
Yeah.
I'm going to go have an ice cream. We'll word for this one, because I didn't think I was doing a real stumper here. So the question was, in 1977, a small group of researchers at Brookhaven National Lab, they changed their detector to measure muon pairs rather than electron-positrons. I guess it gives you a cleaner sample, less background. Muons are things which hit you over the head. Actually, they do that all the time.
Yeah.
They're easy to see, and they got much larger sample. When they put it together, they got this beautiful spectrum with a large statistical bump in it, actually a few bumps, because there are excited states.
Yes.
And that bump was of a particle called the upsilon, I guess.
Yes.
Is that right? And that upsilon is made up of?
A B quark and an anti-B quark. So it's the bottomium.
It's the bottomium, because it's a beauty quark and an anti-beauty quark. And when you put beauty together with anti-beauty, you get a bottom. You get bottomium. So that's what they found. The leader of the team was a young Leon Letterman from Columbia University. That young Leon Letterman also was not necessarily the author. There's been different discussions about this, but the book that he wrote ended up being called, for one reason or another, the God particle. And we're stuck with that phrase, even though absolutely every single particle physicist cringes when they hear that phrase, and we do not want the Higgs boson referred to as that, for any reason, right?
Well, in LHCb, we're happy it's not our problem.
Yeah. Yeah, you don't deal with that.
Yeah.
Okay, guys, I want to thank you guys very much for joining us from Edinburgh. I'm sorry, I hope we didn't take you away from any important talks.
Well, thank you.
Thank you.
And now you can get back to the talks and enjoy them. And thank you very much, Tara, for joining us from beautiful, sunny Liverpool. Tell us about, give us our questions. And I think we're going to conclude with this is our last hangout for the season. We promised you last time we were going to move to a better facility, and we didn't arrive at that yet. But we're going to try still to get a facility and to give you some more tours to show you things that are going on at CERN when we start our next series. But after the summer, everybody enjoy the summer. Have a great time. Get tan. Do some multi-photon absorption out at the beach. And and I got Kate. And I thank Kate Carla for being here, our entertaining producer, and acting as the director as well. Achintia couldn't be with us, but he will be back with us when we come back again. Okay? Thank you, everybody. And we had a studio audience, by the way, studio audience. Thank you for coming here. There are summer students here, and they're going to be here for another 3 weeks, I think. Yeah. Enjoy yourselves. Bye-bye, everybody. Take care.
Bye.